Okay, welcome to another video of probability series. And in this video, I will talk about independent random variable, but I want to talk a little bit about joint distribution that connect from the previous video. So uh, definition 1.8 will tell us about what is joint distribution. So the joint distribution of several random variables. In the previous video, we talked only single random variable, but in this case, we have several random variable that the number of random variable is more than 2. So more than or equal to 2. Psi1, the random variable as psi1 until psi is a probability measure. It's a probability measure that denoted by P of psi1 until psi on N, such that P psi1 until psi of B is equal to P of the set psi1 until psi belong to B. B here it is the subset of the Borel set, but not a Borel set of R anymore. In this case, Borel set it is Borel set of Rn because we have a n random variable. So similar to the previous video about probability density function, if there is a Borel function, the Borel function here I denoted by small f of psi1 until psi and it is a function from Rn to R. And the previous video it is from R to R, and such that the probability function can be represented as the integration, the multiple integration of the Borel function f psi1 until psi. So in this case, the Borel function f psi1 until psi, we call it the joint density function of the random variables psi1 until psi. Okay, so now I go further to another section about conditional probability and independent. So the first definition, in definition 1.11, I will talk about the conditional probability. So for any event A and B, which is belong to the sigma algebra F, such that P of B not equal to 0. Probab of the event B is not equal to 0. B here is not a subset of the Borel set anymore, but in this notation, B it is an event, and the conditional probability of the event A given event B is defined by, this is the notation of the probability of A given B. It is equal to the probability of intersection between this event between A and B divided by the probability of the event B. So from this identity, we can also derive that P of A intersect B, it is equal to P of B multiplied with P of A given B. And we will use this form to connect with the independency of two events of a sigma algebra in the next definition. So let's go to the next definition. In definition 1.12 is that if we have two events AB, as the previous definition, if we have two events AB, we call these two events are independent. These two events are independent if the probability of A intersect B, it is equal to the probability of A multiplied with the probability of B. So it means that in the case of the independent event, the probability of A given B, it is equal to the probability of A if A and B are independent. But if A and B are not independent, we still use this identity. It means that the probability of A intersect B equal to probability of B multiplied with this probability, not this one. So, okay. Now we go to like in this case we use only two even, so we can also extend it to the case that we have n even. We have the even more than two, which is all even are belong to the sigma algebra F. So we can say that even A1 until AN, which is the element of the sigma algebra F, are independent if the probability of intersection of those events from AI1, AI2 until AIK equal to the multiplication of the probability. We change the notation A1 until AN to I1, I2 until IK. In this case, the index I1, I2 until IK is between 1 and less than or equal to n. It can be less than n or it can be equal to n. So this is the extension of the first one. So now we go to the random variable. So in the probability space, omega fp, two random variables psi and eta are called independent if for any Borel set AB. In this case, the notation B, it is the subset of the Borel set. AB is belong to Borel set of A. The two even psi belong to A and psi belong to B are independent. And we say that this one we use two random variable first. And what does it mean for this statement? So it means that we know already that the random variable, it is a mapping from omega to R in this probability space, and the random variable psi have to be f measurable. Have to be f measurable function. So go back to the definition of f measurable. It means that for any subset of the Borel set of R, the set psi belong to A is belong to the sigma algebra F. And another random variable eta, in the similar case, the set of eta belong to B, it is belong to F. So it means that this one, it is an even in the sigma algebra F, and this one, it is another even of sigma algebra F. So if these two even are, are independent, it means that the random variable psi and eta are independent random variable, because like it connect from the definition, the previous definition 1.12, that AB, it is uneven. So in this case, this one is uneven and this one is in another even. So these two even are independent according to the previous definition if the probability of psi belong to A intersect with probability of psi of eta belong to B. These two even is equal to the probability of psi belong to A multiplied with probability of psi of no psi eta belong to B. So in this case we can call it. So in this case we can call the random variable psi and eta are independent random variable. Okay. So we have yes, in another notation we can also write as like uh, by using inverse function psi of A, okay, intersect with psi of B. We can use this notation also, because I read in some book they use this notation, but no problem in this case. And it's equal to psi minus 1 of A in multiply with the probability of eta minus 1 of B. So what I try to tell you that from the definition of the random variable and using the definition 1.12 of the independent event in a sigma algebra, we can derive the independency of two random variables. So this is the concept of independent random variable. Okay, and moreover, we can get some like consequence from this definition. Like when we have two random variable x and y are independent. So the the density, the joint density function of x and y, it is equal to the joint, the density function of the random variable x multiplied with the density function of the random variable y. But if it's not the independent random variable, we cannot use this identity. And also there are some like consequence from this definition about the covariance of two random variable equal to 0 in the case that they are independent and expectation something like that. But I think it's beyond the scope in this video. So thank you, and see you in the next video.